Okay, thank you. Thank you very much again, Roberto, for this kind invitation to this very interesting conference. Um, Interesting topics, very competent speakers, and a very good organization. I will talk about a topic that I've been working on since several years, and together with my colleagues from the geomorphology group of the Italian National Research Council Research Institute for Geological Protection, based in Perugia, and in particular, let me talk my colleagues Maria Teresa Brunetti, Massimo Medillo, and Silvia Peruccacci, because most of the work you are going to see we have done together. Just a brief introduction. We already know everything. Landslides are very different phenomena. Natural induced, human induced, of different types, different size, different depth, different movement, different velocity. And for this high variability, the landslides are very difficult to be predicted. Most of the landslides are induced by rainfall, and in some cases, just one meteorological event can cause up to several thousand landslides. Also, in a very few in a very few times. This is a case study we addressed with my colleagues here in Perugia of an extraordinary rainfall event that occurred in September 2022 in central Italy, and an extraordinary rainfall event with a V-shaped convective system with a peak of measured rainfall of more than 400 millimeters in 9 hours recorded by a rain gauge. This event triggered so many landslides, and we manually mapped into the field more than 1,700 in a relatively small area. This is to say that to predict rainfall-induced landslide and mostly work at a regional scale, we need accurate landscape information, accurate rainfall measurements, objective and reproducible approaches, uncertainty evaluation of such approaches, and also validation of such methods. First of all, collecting accurate landslide information. This is a crucial action for landslide prediction and forecasting. And for this action, we need standardized methods and accurate information. But we have to be aware that information on landslides is often difficult to retrieve and not fully reliable in terms of completeness and temporal and spatial accuracy. We addressed this topic here in my institute, and defining and then using a rigorous approach, we have compiled a catalog named Italica, the Italian Rainfall-Induced Landslide Catalog, which lists more than 6,000 records of information of rainfall-induced landslides occurred in Italy. We searched the information mostly on national, regional, and local newspapers, on blogs and online sources, on technical reports from, as an example, fire brigades, and also Italian railway network company, the company that managed the network. And we also use an automatic search on the internet, combining different terms related to weather conditions and landslides in using Google Alerts. And after a long search with so many years of work, we collected this data. And for each information collected in our catalog, we stored an ID for sure, a bibliographic reference, an information source, type of the landslides, and accurate geographical and temporal information, longitude, latitude, day, month, and year, and time of occurrence. All the landslides are mapped as points, and with an associated geographic accuracy. Indeed, we assigned to each record a geographic accuracy class based on the area over which the landslide realistically occurred. So we passed from a very high accuracy, when we know exactly the landslide location, to a high accuracy when we know the location with an approximation lower than 1 square kilometer, and then medium, low, and very low. But the lower cases are represented in very few points. Also, we consider the temporal accuracy. We have so many landslides for which we know the time of occurrence, hour and minutes. Then for some landslides, we know just the part of the day, and for some landslide, we know just the day of occurrence. We discarded all the information in which we were not able to define the day of occurrence of the landslide. And after this work, we have now this catalog, more than 6,300 records of rainfall-induced landslide occurred in Italy between 1996 to 2021. This is overall the geographical distribution, with some regions with more information than others, also thanks to some agreements we had and we are having with some regional administration. Looking at the geographical and temporal accuracy, we can say that for like 20% of the catalog, we know exactly the coordinates of the landslide. For half of the catalog, we know the location of the landslide with an uncertainty lower than 1 square kilometer, and go on. The temporal accuracy also is very high, because for half of the catalog, we know exactly the time of occurrence. For 1 quarter, we know just a part of the day, and for another quarter, we know only the day. And looking at that temporal graphs, we can see that both geographic and temporal accuracy have improved over time, thanks to also an improvement in the quality of information sources, but also in more, say, accurate work by all the operators that have done this work. This catalog is freely downloadable. This is I'm going to show you, this is a data description paper published in Earth System Science Data. You can download with this QR code, and you can download the whole catalog from Zenodo with all the information I've told you now. Pretty downloadable, and we are very happy if anyone can use this data set for any kind of application. At the beginning, I said we need accurate landslides information, but we need also accurate rainfall information. And in Italy, we have a very good network from the Italian National Civil Protection Department, but we also have some regional networks. And thanks to several agreements from my institute to all these institutions, we can rely now on more than 4,000 rain gauges, well distributed all over the Italian territory, and providing rainfall data with hourly or sub-hourly time resolution. After we collect landslide information, rainfall measurement with a very good accuracy, we need to define objective and reproducible approaches for defining any kind of prediction tool. So if we are using rain gauges, we need to define a rain gauge representative for any landslide point we have in our catalog. And so this is and also this process should be objective and reproducible. And also the rainfall event reconstruction should be objective and reproducible with some parameterization and some rigorous procedure. And also the definition of any prediction model, as an example, rainfall threshold should be objective and reproducible. In this case, let me show you very briefly the method we are using here, and it was also previously defined by my colleagues in my group. This is the frequentist method that is based on power law equation linking cumulated rainfall and rainfall duration of all the rainfall conditions that were defined in an objective way and were considered likely responsible for the landslide in a given area. Once we draw these points in a log plane, we can draw the best fit line, and so we can calculate the differences between the empirical value of cumulated rainfall and the modeled values of the cumulated rainfall given by the best fit, that is a line in a log-long plane, but is a power law function. Once modeling these differences, after modeling these differences with a kernel density approach, we can also apply a statistic model, as an example, a Gaussian function. And in this way, we have the distribution of such differences, and so we can calculate thresholds at different non-exceedance probabilities at any percentile, just by simply shifting the best fit line by a quantity equal to the differences between the median and the percentile in the Gaussian curve. As an example, the 5% threshold leaves below itself 5% of the empirical point with which it was defined. We also evaluated the uncertainty related to these parameters, and so we provide not only a simple equation, and not only a simple line, a simple curve, but a range of variation of the threshold. And this is very important, and we evaluated that such uncertainty range, uncertainty area, is linked to the size of the data set, and also the quality of the data set, but also is linked to the temporal resolution of the rainfall data used. And indeed, passing from hourly data to daily data, for example, we obtain a very significant increase in the threshold uncertainty. This procedure for threshold calculation, but also all the procedure for the definition, objective definition of rainfall conditions likely responsible for landslide triggering, is now included in an automatic tool named Control-T. Calculation of threshold for rainfall-induced landslide tool is a tool is a code written in R, open source software, that needs in input just rain gauge data and landslide data. There is to say, it needs in input the location of the rain gauges and continuous rainfall measurements, preferably at the hourly resolution, and landslide data. There is to say landslide location, landslide time. This tool produces as an output all the rainfall events in a given area and in a given time, rainfall condition responsible for landslide, and rainfall threshold. Also, this tool, which was mostly work by my colleague Massimo Melillo, is freely downloadable from Zenodo. The tool is mainly divided in three main logical blocks. The first one just need the rainfall data and allow the reconstruction of rainfall events by means of a rigorous and objective procedure. The tool needs in input a couple of parameters. There is to say the length of a dry period needed to separate two consecutive rainfall events, and also the definition of the length of the seasons, dry and wet seasons in a given area, in order to vary the length of the dry period. And after this, the tool can produce in output all the rainfall events from all the rainfall series. And the second block use also the information for related to the landslide location and days of occurrence in order to select first a rain gauge representative for the landslides, and then all the rainfall condition responsible for the landslide. And the final block allows the calculation of the rainfall thresholds. This is a case study we did in Italy, using only a part of the catalog that I showed you before. So we calculated different thresholds, different non-exceeding probabilities, and also we calculate thresholds not only for the whole Italian territory, but for several subdivisions of the Italian territory: a physiographical subdivision, lithological subdivision. We also considered soil, land cover, climate, meteorology, that means mean annual rainfall, in order to investigate how all such environmental factors can influence the triggering conditions for rainfall-induced landslides, and also how the thresholds vary in different environmental subdivisions. And an interesting result was obtained for the threshold for different meteorological domains. Calculating the threshold for all the points located in areas with different mean annual rainfall, we obtained that the thresholds for defined for area at increasing mean annual rainfall were higher and steeper. So this means that the landscape adjusts to the meteorological conditions. So where a landscape that usually receives more rainfall during the year needs a higher and more intense rainfall event on average to trigger a landslide. And this is also another important consequence, because we have to be aware that where meteorological regimes will change, also in response to, particularly in response to global warming, all the predicting tools and systems need to be adjusted and adapted to such changes. And this result gives me the opportunity to talk about another application I did, as always in Italy, but only considering a region in southern Italy, Calabria region, where I come from, and using a long-term catalog of landslides dated back from 1921 to 2010, so a 90-year period of information. And daily data in this case, I reconstructed around 1,500 rainfall events with landslide during the whole 90-year periods. And I evaluated the changes in the triggering condition, but also in the spatial and temporal distribution of such events, of such rainfall-induced landslide in the three 30-year periods: 1921, 1950, 1951, 1980, 1981, 2010. What was found was very interesting, because was found a changes in the spatial distribution of the landslide in the three 30-year periods, a change mostly in the last two, because it was the two periods with more data. A change in the monthly distribution of the rainfall events with landslide, and also a change in the triggering condition. Indeed, the triggering conditions were calculated by means of rainfall thresholds, and what we observed was that there was a change in the rainfall thresholds. This change was observed both considering only the events occurred in the three 30-year periods, so 1921, 1950, 1951, 1980, 1981, 2010, but also considering a moving window of 30 years by a step of 5 years, so allowing a more continuous evaluation of such changes. And what we found was a rotation of the threshold, and so a changes in the triggering conditions of such phenomena in response to a change in meteorological features, and so in climatic, given the long-term evaluation of such changes, so we can say given to an observed change in climate in that region. And after that, I can conclude my talk, just summarizing some challenges that I think we can address in some way. First, I have talked about empirical regional scale approach, and I think that such approaches can be applied to different study areas where similar data is available, in order to have a quantitative comparison of the results. And anyway, and moreover, empirical and regional scale approaches can be also combined with climate modeling chain, so with a climate projections, to evaluate both changes in the past and in the future. This tool, empirical thresholds, is can be considered a simple model, but it needs a rigorous and objective and reproducible theoretical basis and an accurate data set to be defined. And I think is a very useful tool to predict rainfall-induced landslide. For sure, the robustness of the thresholds depends on the empirical data set, and the robustness of the threshold should be evaluated by means of a validation against an independent data set. Independent, but that can be considered an independent data set both in time or a data set that were collected from different sources, for example. And moreover, also the uncertainty of such tools should be always evaluated and quantified. In conclusion, we can say that the prediction of rainfall-induced landslide in this changing climate that we are living, changing world that we are living in, is possible, and for sure can contribute to mitigate landslide risk. For sure, climate change makes the prediction more challenging, and for this reason, we need rigorous approaches based on accurate and complete landslide records, as I think the one that I show you, so collected with standardized and rigorous procedures. We need also accurate and complete rainfall and climatic data, rigorous tools again, in order to reduce the uncertainties and provide reliable results. And with this, I've concluded my talk, and I want again to thank you for your attention and Roberto for this kind invitation.